Okay, so we'll continue to do problems on fins. So in this problem, we have a rod protruding normally from a furnace wall that is covered with insulation of thickness L insulation with the length L0 exposed to convection with ambient air. We want to find an expression for the exposed surface temperature T0 as a function of the prescribed conditions. And then we will see if a length of 100 millimeters will meet the specified operating limit of T0 smaller than 100 degrees. If not, what are the design parameters that we can change? Okay, so this is a typical design problem. You know that in general, for a furnace, the surface temperature is really high. So you have a wall temperature of 200 degrees, which can burn people. Okay, that's why we need to insulate this wall. Okay, plus we need to evacuate heat as much as possible. So in this case, what we did is first we considered a certain insulation in order to reduce, if you want, heat transfer from the wall to the surrounding. And here we want to have a temperature at this level that is acceptable. We need to have it smaller than 100 degrees. So here we are working on two strategies. First, we put insulation in order to reduce heat transfer from the furnace wall and reach a temperature that is acceptable here. Plus, to help having a low temperature at this level, we extend the fin. Okay, so here our fin will start from the furnace wall, but in the first part, it is within an insulation. Since it is covered by an insulation, the fin in this part will not be subjected to convection. So you only have conduction. Okay, and because you are insulating, you need to reduce the conduction flux, because if you have a low conduction flux, this will lead, okay, so if you have high resistance to conduction, this will lead to a smaller temperature at the surface. So you need to reduce, if you want, conduction flux in the insulation, but you want to increase as much as possible evacuation from this side, from the exposed side of the fin. So these are the two opposite effects that we have. That's why in this design, it's not like a conventional fin. And for the conventional fin, it's good to increase the conductivity. Higher the conductivity, the better is. But here you have two aspects. Okay, if you increase the conductivity, it's true that the heat evacuated in this part, which is the part exposed to T infinity, will be better. But also you have the heat conducted through the insulation will be higher. So you have here two opposing effects for the conductivity. It's not a normal fin here. That's why we need to consider a certain design to optimize, if you want, the value of conductivity of the fin. And also we can optimize the length L0 to have. So larger is L0 in general. The better is until a certain limit. If you remember, we studied the solution for an insulated tip. For a very long fin, we said we can consider a certain equation, but if the tip is not insulated, we consider another equation, the one including tan hyperbolic. Okay, and we can look at which lengths for which lengths we can consider that it will behave as an infinitely long fin. It's the one corresponding to 99%, if you want, of when we reach a certain temperature profile equal to 99% of the one in case of insulated tip, we can consider that this length is enough, because if we increase the length more, no additional, the additional heat that will be lost is really negligible. Okay, so we will work on these aspects in this problem. To start with, okay, if we want to determine what is the temperature T0, okay, we need to conduct analysis. What do we know? We know the temperature at the wall, which is 200 degrees, okay? And we know T infinity, which is 25 degrees. So we have several approaches. We can use equations as you can write the equation in insulation. You have only conduction. So in insulating part, we can say that Q conduction is equal, okay, to the conductivity of the material times cross-sectional area of the fin, okay? We know that in pure conduction, we have linear variation of temperature. So in the insulating part here, in the part covered with insulation, the temperature will drop in a linear way, okay? Because you don't have loss from the fin towards the outer side. So heat will be conducted through the fin, okay? So if I consider my fin, in the first part of my fin, I don't have heat convected to the outer part because I have insulation. So no heat can propagate in this direction. Only heat will travel through my fin by conduction, okay? So that's why I can say that Q conduction is equal to K times cross-sectional area of my fin times, we know that T wall will be larger than T0. So it's delta T over L. So T wall minus T0 over L, okay? But here we don't know the value of Q conduction. Okay, we don't know the value of Q conduction. We need to say that this Q conduction is equal to the one that will be evacuated from the fin. Okay, and if we consider, if you want, the case, we can use corrected lengths here in order to use the formula for Q fin or with insulated tip. Okay, so we can say that this is equal to Q convected from the fin, okay, using the corrected lengths. Okay, you can use equation, you can use, if you want, just this analysis with equation, but also you can use thermal circuit resistances. Here resistances, as usual, will simplify things for you. Okay, so you can say also, instead of just writing equation form without using the resistance concept, another method is to use the resistance concept. And the resistance concept will state the following. I can draw a thermal circuit. In the first part, what do I have between T wall and T0? I have the resistance of insulation, which is only resistance to conduction. And the form of this resistance is L insulation over conductivity of the material times cross-sectional area of the fin. So here, for example, it's a circular fin. So AC is pi d square over 4, okay? This is for the resistance of insulation. If you remember, last time we developed together an expression for the resistance of a fin. If you don't want to use the concept of corrected lengths here, okay, you can use the accurate formula. To not use corrected lengths, you can use the exact formula by considering from the table what is Q for a fin of a certain limited length that is not insulated. If you go to your table, okay, you can see that the expression of QF is theta base times M. What is M? If you remember, it's radical HPKAC times tan hyperbolic ML0. So if you use now the resistance of fin, what is the resistance of fin? It's theta B over Q evacuated from the fin. Okay, you can simplify theta B. And then you end up with the resistance of the fin is 1 over radical HPKAC times 10 hyperbolic ML0. If you want to use the corrected lengths concept, okay, then you don't consider 10 hyperbolic ML0, but you should add the corrected lengths corresponding to your circular rod. Okay. Here, this is more accurate because this will give you exactly the expression of Q fin. That is not considering any correction, because here in this formula, this is the solution whenever you don't have insulation at the tip of your fin. So since you have the exact solution, you can use it. Okay. If you simplify theta B, you can calculate the resistance of the fin. And as we said here, P represents the perimeter of the fin, so it's pi d, and AC represents the cross-sectional area of the circular fin, which is pi d squared over 4. So now, this is very simple. So this is much easier if you want than writing this. Both methods will give you exactly the same result. And here, you can replace Q convection, okay, by the expression of Q fin. What is Q fin? It's the expression here. It's equal to Tz, theta base, which is T0 minus T infinity. Okay, times the convective coefficient H. Sorry, times M. This is M. Okay. So times radical HP KAC times 10 hyperbolic ML0. You get this from the table. If you remember the table we have seen last time, okay? You just have to go to your table and see for the case of a fin that is not insulated at the tip, what is Q fin? You can read this expression. So just to replace theta B times radical HPK AC times 10 hyperbolic, okay? So if you use this this equation, you have in this equation the only unknown is T0, because T wall is known and T infinity is known. So you can solve for T0. This is if you use this this method. If you use the electrical circuit method, okay, using the electrical circuit method, you can say the following. You can say, I know the value. I know the value of our insulation and I know the value of our fin. Okay, I know the resistances, so I can calculate Q. I can calculate the value of Q by saying that QF is T wall minus T infinity over summation of resistances. Okay, and once I get a QF, I can apply between T wall and T0 or between T0 and T infinity. So it's equal to T wall minus T0 over our insulation. And it's equal also to T0 minus T infinity over R fin. Okay. So now you can solve for T0. Any question on this part? Okay. Now, if we do the calculation for the given values, we get that T0 is 109 degrees. This means that we didn't meet the expectation. We want T0 to be smaller than 100. And they are asking us what can be the strategies, okay, to have a lower temperature at this level. Okay, so for example, if you impose T0 to be 100, so you can work in the opposite way. If you say, let me impose T0 to be 100, if I consider the same length of fin, I can ask myself, what should be the conductivity K of the rod in order to reach this temperature? Okay, and here, you cannot say that I should increase K or decrease K. As I told you, here you have two opposite effects, okay? It's good to decrease the conductivity of the rod to reduce the heat transfer through the insulated part, okay, through the fin and the insulation part. But it's good to increase the conductivity on the other hand in order to enhance convection from the fin part exposed to the surrounding. So this is why here K need to be optimized. And you have a value for K. And if you draw, for example, if you draw T0 variation with K, you will find that you have a certain minimum. T0 will be minimum for a certain value of K. This is the value, so K can be optimized in this way, okay? Here, since you want T to be 100, you can put T0 equal 100 and solve for which value of conductivity will give you this 100 degrees, okay? So all we have to do now is to go back to the same equation. You still have the same equation here. And our insulation is function of K, okay? And our fin also is function of K, okay? So if you replace in your equation, you can find out what is the value of K that will give me T0 equal 100. So you replace now T0 by 100, and the only unknown in your equation here in QF equal TW minus T infinity over sum of resistances, the only unknown is K. You can solve for the value of K, which will give you a temperature T0 equal to 100 degrees. If you solve for this value, okay, you get that K should be 14 watt per meter Kelvin, which is much smaller than the conductivity that you are using here, okay? So we can say then that to select an appropriate material, we go to a certain table of materials and we select a material having this value of K. For example, you can select here stainless steel alloy, which is characterized by a conductivity of 14 watt per meter Kelvin. Okay, so here we can understand, if you want, why here we had a value of K lower than 60. In general, when you have a fin exposed entirely to the free environment, it's good to increase K, because when you increase K, okay, you can evacuate more heat. But in this case here, you have two opposite effects, okay? You need here to reduce, the heat transfer through the insulated part, but you want to increase the heat transfer through the fin. So since you have these two opposite effects, you cannot find actually how K will affect your result unless you do calculation, okay? So this is for this part. Now, what can we do also? We can try to increase the length of the fin, okay? So you can do the following, as we did last time, if you remember. You can say, when the lengths tend to infinity, I can consider that I will approach the solution of a normal of a fin of infinite length, which is just Q fin equal theta base times radical HP KAC. So 10 hyperbolic will tend to 1, okay? And of course, it will tend to 1 at infinity. So I can take what value of length L will give me 10 hyperbolic equal to 0.99. Okay? So I solve for the length L exposed to the outer environment. That will give me 10 hyperbolic equal to 0.99. And in this case, I can say that for this value, okay, I can consider that it's useless to increase the length of the fin more. Okay, so I can investigate what is the value of L0. If L0, for example, if I solve, okay, and I get that L0 is here I am using, for example, 200 millimeter. If I get L0 400 millimeter to have to reach 0.99, I can say I can increase this length up to 400 millimeter to enhance evacuation of heat. Okay, while in the other on the other scenario, okay, if I want to reach if I get, for example, instead of 400, if I get 100 millimeter, this means that if I extend my fin beyond 100 millimeter, it's useless. Okay, so in case you get the value of L for which 10 hyperbolic equals 0.99 larger than 200 millimeters, you say, let me increase the length of my fin that is exposed to the outer environment. If you get it smaller, you say it's I don't need to add any additional lengths because this will not evacuate, it will not help me into evacuating heat. Okay, so this is the idea here. So this is a design problem that can help us to understand the different, if you want, parameters effects on our T0. So our purpose is to get T0 as minimum as possible. So we can work on two aspects. We can work on better insulation here, okay, and better convection from the fin in the other part. That's why we can optimize, if you want, the conductivity of the material, we can optimize the length of the fin, etc. Okay? Any question on this?
No.
Okay. Okay, we still have a problem that we didn't solve. Let us do it.
Hello دكتور.
Yes, hello. Yes, tell me.
دكتور معقول بس تنزلينا بليز الفورمولا شيت قبل بوقت لنعرف شو بعد عنا اشياء نحفظهم وشو لا.
Yes, sure, sure.
Thank you.
Welcome. Okay, let us solve the following problem. A radioactive material of thermal conductivity K is cast as a solid sphere of radius R0 and is placed in a liquid bath for which the temperature T infinity and convection coefficient H are known. Heat is uniformly generated within the solid at a volumetric rate of Q dot. Obtain the steady state radial temperature distribution in the solid, expressing your result in terms of R0, Q dot, K, H, and T infinity. Okay, so in this problem, we have a spherical geometry. So we need to consider the equation in spherical coordinates. And we have steady state and uniform generation. If we go back to our differential equation, in this case, okay, first it's steady state. So the term that is del T by variation of temperature with time will cancel out. You only have variation in radial direction, okay? So you have 1D case, and you have Q dot. So if you simplify your terms, you end up with the following equation: 1 over R squared, derivative with respect to R of K R squared dt by dr, plus Q dot equals to 0. Okay? So now all I have to do is to integrate this equation twice. If I integrate the first time, so first I take a Q dot to the other side, I get minus Q dot. Then I multiply by R squared to be able to integrate. So I get here minus Q dot R squared. And since the conductivity is constant, K, I can take it outside of the derivative, and I can here divide by K. Okay, so I end up with the following relation: derivative with respect to R of R squared dt by dr is equal to minus Q dot R squared over K. Now, I am ready to integrate the first time. So when I integrate the first time, I get minus Q dot R cubed over 3K. And I don't forget to add constant C1. So plus C1. This will be equal to this term, which is r squared dt by dr. Now, to perform the other integration, I should divide all terms by r squared. So if I divide by r squared, I get here minus q dot r over 3k plus c1 over r squared. And now I'm ready to do my second integration. If I integrate again, I have the temperature profile given by the following relation. Minus q dot r squared over 6k minus c1 over r plus c2. Now, all I have to do is to solve for constants c1 and c2. You know that to solve for these constants, I need two boundary conditions. Can you tell me here what are the boundary conditions to use in this problem to solve for c1 and c2? What are the conditions that you will use to solve for c1 and c2? First, here you have symmetrical heat propagation, okay? You have, sorry, you have here generation of heat, okay? And this generation of heat will propagate by conduction in all directions to be evacuated at the free surface of the sphere. So you can say here that because of this symmetry effect, the maximum temperature will be at the center of the sphere, and it will be reduced due to conduction through the radial direction. So condition one is that the derivative of T with respect to R will be equal to 0 at R equal 0. So now, if we go to dt by dr expression, and we replace if we go to this relation here, just before dividing by r squared, okay? Because you cannot divide by 0, okay? So before you divide by r squared, what was your condition? Your condition was r squared times dt by dr equals to minus q dot r cube over 3k plus c1. So if you replace r by 0, you can say that c1 should be 0, okay? So from here we deduce that c1 is equal to 0. This is for the first condition, okay? Now, second condition is at the free surface. As usual, if you take is a thin control volume at the free surface, what can you say? You can say that heat will enter this control volume by conduction and will leave the sphere by convection. So condition 2 will be that Q conduction, and pay attention here, Q conduction is varying within your sphere, okay? So Q conduction at R0 at the outer surface is equal to Q convection to the outer environment. And we know that how we write the expression of Q conduction, it's minus K times the lateral area of the sphere at R0, which is 4 pi r square or pi d square, times dt by dr at R0 is equal to the convective coefficient H times T surface minus T infinity. So times T R0 minus T infinity. Okay. And now, if you replace, what is dt by dr at R0? If you go back to your equation, this is dt by dr. So if you replace at R0, you get minus q dot R0 over 3k. And C1 is already equal to 0. Okay? So all we have to do is to replace. If we replace in this equation, we get the following. Of course, don't forget to multiply by the area. Area, lateral surface of the sphere, yani area at R0. And here the area will cancel out. So you can cancel out the area, and your equation will be as following. Minus K times. Now we need dt by dr at r equal to R0. So we replace in this equation, as we said, we replace r by R0. So it's minus q dot R0 over 3K. So K will simplify. And minus minus, so you can put plus. So plus Q dot R0 over 3 is equal to convective coefficient H times TR0. To get TR0, I replace here TR0 by its expression. So it's minus Q dot R0 square over 6K. We already determined that C1 is 0. So plus C2. And this condition will allow you to calculate the value of C2. So C2 is simply, of course, don't forget to put TR minus T infinity, because it's TR0 minus T infinity. So C2 is equal, if I take H to the other side, it's Q dot times R0 over 3H. Okay, plus Q dot R0 square over 6K and plus T infinity. So in this way, I solved for the value of C2. If I replace C2 in my equation of temperature, I get the general equation of temperature in my sphere, which is of the following form. So TR is Q dot over 6K R0 square minus R square plus Q dot R0 over 3H plus T infinity. So the temperature is varying as a second degree function of the radial position. And this will justify that if you solve for the conduction rate, it will not be constant, okay? The conduction will be proportional, and you can write its expression. The conduction will change because of generation. It will change with R, the radius R, okay? Any question on this?
No.
If you want to evaluate the flux, if you want to evaluate the flux of conduction, Q second conduction, you just have to apply the formula. Q second conduction, it's minus K dt by dr. Okay, and dt by dr is minus q, you get its expression from here. It's minus q dot r over 3K, so you can replace it. So it's equal to minus K times minus q dot r over 3K. And K will cancel out. So Q second conduction is plus Q dot R over 3, okay? And if you want to get the rate, you multiply by the area. And the area at each location is pi R squared, okay? It's, sorry, pi D square, yani 4 pi R squared. Okay, so yeah, I'll open a new session.